Thank you for organizers for giving me this opportunity to present recent work on this anomalous diffusion in random dynamical systems. I'm Yuzuru Sato from Hokkaido University. In the program, my affiliation is in University of Tokyo, but it's wrong, from Hokkaido University. This work is a collaboration work with Rainer Craig's at Queen Mary University of London, working on diffusion and anomalous diffusion. So this is the outline of my talk. We'll talk about random dynamical systems and noise-induced phenomena. This is a brief review. And I will also review deterministic diffusion studies, classical one. Then I present anomalous diffusion in random dynamical systems, and I summarize my talk. Right. Okay, so random dynamical systems is given by the combination of two systems, theta and phi. Theta is the model of noise or model of environment. And then phi is a model of dynamics. And the example can be given by this simple random map with additive noise, with deterministic map. And the state space is this probability space and deterministic space, product of that. But we are interested in the projection of this entire state space. Right? And then we discuss about the phenomena in the space X for model of dynamics. So for this kind of systems, we can introduce attractor concept and its stability concept like Lyapunov exponent, similarly to the deterministic dynamical system theory. In random dynamical system theory, the random attractor is given as a function of omega. Omega is noise realization or noise or input realization. So depending on noise realization or input sequence, we have different attractor in general. And we will analyze all possible attractors for all possible noise realizations. And for that kind of attractors, we can also define the Lyapunov exponent and discuss its stability. And this Lyapunov exponent in general is again the function of external force or noise, but similarly given as the classical case. So, right. So this is a simplest example of RDS. Solvable one, Langevin equation for Ornstein-Uhlenbeck process. And in terms of random dynamical systems theory, the solution of this stochastic differential equation is given in this way. The attractor is random point attractor x, depending on omega. And invariant density is actually solution of Fokker-Planck equation of this. And it's given by this form, totally solvable. By using lambda and sigma. And the Lyapunov exponent is, in this case, minus lambda. And it's not a function of omega. It's, for almost all omega, we have minus lambda as a Lyapunov exponent for this system. So this is the interpretation of the Langevin equations in terms of random dynamical system theory. Okay. So we could extend this to the higher dimensional systems, like this deterministic part can be replaced by standard Lorentz equations. We set standard parameters. We have strange attractors. And in SDE, we also have a kind of random attractor. It is sometimes called random strange attractor. It's a function of omega, again. But the definition of strange attractor in this system is almost same as the classical one. So we call this random strange attractor. And the phenomena generated by this system is sometimes called the stochastic chaos. The chaos in stochastic process can be defined in this way. Right. So although this is quite new mathematical concept and structure, and it's, the mathematical structure is not known precisely, but we recently applied this concept to experimental time series analysis for fluid flow turbulence in Kalman flow, and succeed modeling this complicated system and analyze the bifurcation structure. So in that sense, this random strange attractor exists in this in the real world with these reductions. This is a model, stochastic Duffing equation, and this is embedding a Lyapunov spectrum in this case. Right. So this is a collaboration with Brownian and David sitting over there. So my main work is applying this random dynamical system theory to noise-induced phenomena, various types of noise-induced phenomena, like stochastic resonance, synchronization in the Kuramoto oscillator, or noise-induced chaos in the chaotic systems. These are very classical problems from 1980s. Nonlinear physicists mainly working on this. But by using random dynamical system theory, we can analyze this in a unified way. So we take classical noise-induced phenomena problems, and this is a property as random dynamical systems. For example, stochastic, noise-induced synchronization is random point attractor, and there's topological bifurcation. And this is top Lyapunov exponent of the system as a function of noise amplitude sigma. Right. So, and then stochastic resonance is random periodic attractor, and noise-induced chaos is given as random strange attractor. So we will focus on this noise-induced intermittency later in this topic, talk. And this is also observed in many systems. And we analyze this as random dynamical systems context. Right. So in title, I includes these anomalous diffusions. But I explore this noise-induced phenomena in open dynamical systems, like diffusive dynamics. So in this case, this is a schematic view for the diffusive dynamics, one-dimensional. So X is in one-dimensional space, and T, this is T in the time. And then there are, we have many particles, and then it's fluctuate, actually, behave like random walk, and we observe diffusive dynamics with diffusion constant D, for example, 1.2 in this case. And if we perturb this system and adding noise, then sometimes we have anomaly of this dynamics, anomalous diffusion. Diffusion constant becomes 0. So it can be called noise-induced anomalous diffusion. We will discuss this in terms of deterministic diffusion context. And this is one example of noise-induced phenomena in open dynamical systems. So, okay, so deterministic, I will explain the deterministic diffusions from some slides. Right. We start with this periodic Lorentz class, deterministic, energy conservative. And in open billiard system, we have many particles with different initial conditions. Then,
it's Lorentz with a T. That's the other. The other one.
Sorry, yeah, we have two Lorentz. Yeah, this is different Lorentz from Lorentz. Right, again. So in we have some later time observation, we observe this kind of property. So it's distributed. The particle is distributed in the entire space. So this is a model of diffusion as deterministic dynamical system. So we like to have a simple deterministic model for this phenomena. by using one-dimensional map, which is sort of like this Bernoulli map. Bernoulli map is equivalent to coin tossing if we coarse-grain dynamical systems and have symbolic dynamics. This is a well-known fact. And we have open system for Bernoulli map, meaning that for this slope is now more than 2. Then we have escape hole. Then we have chaotic dynamics here, but we have escape hole here, and dynamics escape this way or this way. So this is this correspondence is not exact. This is a schematic view for open billiard. So this is open billiard, the studio billiard here, chaotic, and we have 2 escape hole, and the particle escape this way or this way after chaotic scattering. And this is a model for this motion, abstract model. Right. So next we spatially extend this open Bernoulli map. It's chain of open Bernoulli map. So it's chain of open billiard systems. And the particle start with this area and then go this way or this way, depending on initial conditions. So if we iterate this spatially extended open Bernoulli map, we observe this type of trajectory. So starting near 0, in the long run, we deviate from 0. It is, Yes, it is replaced by random walk. It can be approximated as random walk in some scalings, adequate spatial temporal scalings. This is equivalent to the random walk. So if we have many particles in the first area, this area, we have this kind of dynamics. So this is a figure for the diffusive dynamics. We have n particles, there's n trajectories in the billiard systems. And we observe random walk, many random walk. And the equation of motion of the density P on sample measure is given by diffusion equation with some diffusion constant D. And this D is not explicitly given initially, but we can measure this diffusion constant by measuring mean square displacement, meaning that the fluctuation of the position. This is log-log plot of this time evolution of this mean square displacement. It's on the line. And the slope of this line gives us this diffusion constant. This is the definition of diffusion constant. Right, so in this way, we can use deterministic mappings and to have, for having diffusive dynamics. We could do this as a non-trivial nonlinear map. Right? This map is called the climbing sine map. It's actually spatially extended sine circle map. So we set this parameter A 0.95, and we have this behavior for the many initial conditions, and the MSD is proportional to time t. So this is diffusive dynamics in this coarse-grained macroscopic scales. However, if we use these nonlinear mappings, we have different phenomena. This is bifurcation diagram for the sine circle map. If we choose parameter here, a 1.01, it's about same shape of the mappings, but we observe ballistic motion for this system. It's not diffusive dynamics, it's ballistic. So D, diffusion constant D, it goes to infinity. And other parameter here, this window region, a 1.5, we have localization dynamics. We trapped to a limit cycle. So we have many limit cycles in the lattice, and one of them traps the dynamics. So it's localization. So diffusion constant goes to 0. Right, and then the onset of bifurcations, we could use this Pomeau-Manneville map originally from fluid flow turbulence. And it shows non-stationary behavior. If in this model Z more than Z, you have invariant density, non-normalizable invariant density, and then construct the spatially extended map. Then we have sub-diffusive dynamics, slow diffusion. And then slope of MSD is not linear. It's T3 alpha. This alpha is 0.5 in this case, in this particular case. This exponent, relationship between this exponent and alpha and Z are known, analytically solved, like in Theo Geiser's work. We can have super diffusive dynamics, meaning that it's faster diffusion by using same Pomeau-Manneville map. In this case, behavior is like this. It's almost ballistic, but sometimes we have chaotic trapping, and then again ballistic. So that this exponent alpha is more than 1. It's 1.5, for example. Right. So in this way, if we set different mappings in these models, like climbing sine or Pomeau-Manneville, we can have all type of diffusive dynamics. In this case, ballistic, super diffusive, normally diffusive, sub-diffusive, and then localizations. So by controlling the map parameter, we have all range of diffusive dynamics. So this is a typical study in the classical deterministic diffusions. So go back to our problems in the noise-induced anomalous diffusions. We have a deterministic model. If we provide a stochastic model, we never have this phenomena, because diffusion is random walk and adding noise is again random walk. So it's difficult to have anomaly. However, if we have this underlying deterministic dynamics, chaotic dynamics, like this, and then it modulates in this way, red and blue, this is the extreme example. Can you see the, okay, here. The amplitude of sine circle map is replaced by a random variable. Right. So with this perturbation, this can be, this diffusion vanish, and we observe anomalous diffusion or localizations. So mechanism is very simple. So we further reduce these mechanisms like this. This is our models. The kick amplitude, A, so kick amplitude is a random variable in this way, dichotomy noise. We use this map with probability 1 minus p. We use this map with B with probability p and switch it randomly in time. Then we observe anomaly in the dynamics. Near fixed point, we can have this structure. This one map is expanding, other one is contracting. So we can have model, simplified model in this way. This one is actually A equal 4. A equal 4 open Bernoulli map. And this one is A equal, for example, 1/2. So it's contracting to each fixed point. And dynamics is like this by iterating this map. And dynamics, blue dynamics is generated by this contracting map. Right. So this red one is diffusive dynamics. But if we use this map, both map randomly switched with probability p, then we have mixture of red expanding map and blue contracting map in time. And this system shows this kind of trajectories, like intermittent behavior and anomalous behavior. We need to set P is P star to have 0 Lyapunov exponent. So this P star is critical value. Except this P star, we don't have this behavior. Like this way. So we change the probability P in 0.6 to 0.7. And this is mean square displacement for this randomly switched linear map. If P equal 2/3, then the Lyapunov exponent is exactly 0 for these random dynamical systems. In that case, we have this pink line for MSD, T to the 1/2. So it's anomalous diffusion. And if P is more than that, then we have this blue line. The exponent is 0. It's trapping, localizations. And P is less than this value, for example, 0.6. We have these red lines showing normal diffusion. Our exponent is 1. Right. So we need to set this critical value P equal 2/3. Otherwise, we have expanding or contracting map. In other words, this pink line is achieved by neutral dynamics in average. Red one is expanding in average. Blue one is contracting in average. Pink one is totally balanced. It's neutral in average. Right. And then we observe this. This is numerical observation and approximation as continuous time random walk theories to analyze the aging effect in this MSD and waiting time distribution. The exponent is for MSD is 1/2, and for waiting time distribution it's minus 3/2. And this dot is numerical computations, and the line is theoretical prediction by CTRW approximation. So it's very good agreement for these two systems. Right. And we can also approximate this aging effect with this continuous time random walk theory. So we'll talk about more like mathematical structure for this underlying dynamics in the case of linear random map. This random piecewise linear map, now it's a closed map. It's not open map, but the statistics is about the same. Random piecewise linear map is given in this way. We have Bernoulli shift if P equal 1, and we have a contraction to the origins if P equal 1. But we choose different P, intermediate 0 and 1. We have randomly switched mappings. So we can solve this map in many sense. Like invariant density is given by these step functions. We have explicit formula for this, the step functions. Right. It's known result. And then if we interpret the midpoint of these step functions, we have nice curve. This curve is given by this way. So if C goes to 0, when P goes to 1/2. 1/2 is null Lyapunov exponent point, intermittent point. In that case, C goes to 0, and we have x to the minus 1, 1 over x. So non-normalizable density, which clearly shown like infinite ergodicity or non-stationary intermittency. So good things for this particular example is we can solve entire range of this parameter P. If P equals 0, point attractor. P equals 1, uniformly chaotic. P equals 1/2, we have infinite density. And then lambda time average of the Lyapunov exponent is 0. Ensemble average is not defined in this particular system. And then we have non-stationary intermittency. Yes, please.
What do you mean by uniformly chaotic versus chaotic?
Yeah, maybe it's not a good definition, but this is like same as Bernoulli shift. And this one is not.
Sorry,
This is the same as Bernoulli shift, and this is not. Maybe hyperbolic, non-hyperbolic, but we didn't explain. Yeah. And then this one is 0 to 1/2. We have a contraction in average, and eventually goes to point attractor, but we still have a fluctuation. Right? In this case, totally neutral, non-stationary. And this 1/2 to 2/3, we have this real proof exponent positive, and we have stationary intermittency. Stationary intermittency means unbounded density at the point 0, the stagnation point, with power law. But the distribution is normalizable, so it's not non-stationary infinite systems. It's stationary, but intermittent. Then chaotic and uniformly chaotic. Right. So this anomalous diffusion induced by noise is based on this property of this random linear map. It is based on infinite density and non-stationary intermittency. Otherwise, we don't have anomalous diffusion. So next, we investigate the type of intermittency in this particular random linear map and found that it's equivalent to the on-off intermittency in many cases. So intermittency in deterministic systems is given in this way, in some sense. So this Pomeau-Manneville intermittency is well studied. We have many works. But there's another class of intermittency in two-dimensional map. It's called on-off intermittency. So in this system, unlike this Pomeau-Manneville intermittency, this laminar region is given by high-dimensional object, like line or surface, not point. It's in higher dimensional object. And then we intermittently switch this chaotic region to this laminar region. And we extend this to the network. We have many laminar regions as stable, unstable invariant set, but not stable, give us these laminar regions, and then we have many of that, and then we have networks and chaotic dynamics and the switching between these laminar regions give us intermittent behavior. So it's called in-out intermittency. This is not studied well studied. These are some studies. So as for on-off intermittency, we can have a very simple example, like coupled logistic map, coupled chaotic logistic map, and epsilon is set to a bifurcation point. It's called blowout bifurcation, and Lyapunov exponent is 0. Then we have intermittency, but it's different from Pomeau-Manneville intermittency. This is a behavior, time series, and this is state space. The important thing is the waiting time distribution, the slope of waiting time distribution given by t to the minus 3/2. Right, so this intermittency is typically observed in two-dimensional mappings at the bifurcation point. So it's different from Pomeau-Manneville intermittency in one dimension. So for this, studying this on-off intermittency is done by reduction of two coupled maps, two coupled chaotic maps, and the reduced model of on-off intermittency is sometimes given in this way. And the waiting time distribution is given in t to the minus 3/2. And we can see this model is about same as this random map. Right? So this is, this part, and then this gives us switchings, random switchings. So that we also have this slope exponent of minus 3/2. So exponent and other statistical property is exactly same as deterministic on-off intermittency in random linear map. Right, so this is small but new findings. We didn't realize this random map generates on-off intermittency. So in some sense, random map is similar to two-dimensional map if we regard this noise term as other one-dimensional chaotic dynamics. That's this model. Right, so we tried to apply this concept to other class of random map and to explore universality of this phenomenon. So for example, this we extend the noise to the uniform distribution. The slope is from B to A, contracting to expanding, continuously change given by uniform distribution. We still have same exponent, minus 3/2. Right, so we investigate unbounded noise case, in this case log normal distribution for this slope. So slope of random map is given by log normal distributions. In this case, MSD, similar MSD, and similar or same waiting time distribution, t to the minus 3/2. And finally, nonlinear map, like sine circle map, dichotomy noise. We have, again, same exponent. For MSD, 1/2. For waiting time distribution, minus 3/2. So it's quite robust properties. Actually, we tried to have a different exponent or different intermittency, but we didn't succeed so far. So, like other logistic map or like Nagumo map or some other chaotic dynamical systems, adding noise, tune the Lyapunov exponent 0, they all show these properties. So it's quite universal properties. Right, so this is actually last slide of my talk. We found noise-induced anomalous diffusion, and it's very general context in one dimension, and it is noise-induced phenomena in open dynamical systems. And an anomaly is based on on-off intermittency in deterministic two-dimensional dynamics. And for this underlying dynamics, 1D random dynamical systems with neutrality in average shows on-off intermittency and shows this universal property as intermittency. So I think this example is a very, very simple, in some sense, textbook example, because it's simple, clear, solvable, and universal for most random dynamical systems. So this can be a representative of the model, standard model of intermittency in one-dimensional random dynamical systems. Actually, I'm writing Japanese textbook, and this model is in the textbook. So this is textbook examples. This will be. And then we are working on super diffusive dynamics in random dynamical systems in one dimension, but so far we couldn't find. Maybe some spatial configuration is important or some other property necessarily, but still looking for this other anomaly corresponding to Levy walk. Right. So this is the reference for this entire talk. Thank you very much.
Thanks a lot. That's not good. So comments or questions? Yes, please.
Can you just define the waiting time in your
Waiting time distribution.
Yeah, what do you call the waiting time in your quantum map?
Yeah, waiting time is the time duration near lamina.
Yeah.
Lamina region, lamina, a fixed point.
Okay.
Non-bursting time region. This is distribution of this such duration time. Right, okay.
Comments or questions? I have one. Can you give us a bit of a qualitative feeling of the properties of the on-off intermittency versus the classical intermittency? So So somehow, how can we see signals? Say we look at the time series,
Yeah.
and that's what you would like to see, to have a feeling of how this phenomenon look like. That's why we have a name for it, right?
Right.
So it's not just a relationship; it's a name because we want to see it somehow.
Right.
So can you
Explain? Okay. So this based on this model, couple logistic map. If we have x equal y, then this is one-dimensional map, totally synchronized.
Yes.
That's in this state space picture here.
Yes.
Right? So if x equal y, we stay here, we dropped here. But if not, if slight difference there, we escape from this synchronization manifold. Right? So this is line. Invariant set is given by line, not point.
Yeah, sure, yeah.
And then we escape here and come back here. So that's the property of on-off intermittency. But you are saying that your question is about on-off.
On-off, yes. So yes, the idea that you have a large departure that suddenly that has a very short lifetime, or
right. So it's the problem or the property of this system is in this line we still have chaotic.
yes.
So this is one-dimensional chaotic, and this is two-dimensionally chaotic. So this switch express on-off. They try to express this property. In the Pomeau-Manneville map, the laminar region is a fixed point, right?
Yes, yes.
So stable region, unstable region switching.
So it's like, would you say that is, I mean, I'm just trying to find a qualitative note to it. Something like that, rarely, but you activate like a second instability.
That's right, yeah.
So something like there is a new mechanism that's switched on and lasts
Right.
for a short time. So it's something new, something extra that takes place.
Right, that would be the implication, like variability of degree of freedom.
Yes.
1D,
yes, okay.
2D,
Yeah, that's what
so on and off. Yeah.
Okay, thank you. Yeah. Thank
It can be clearly, yeah,
you.
extended to a large dimensional system. Yeah, so.
Yeah.